All right, we are now on to example 12, where we're going to differentiate the following function. So what we want to observe here, again, is what is the overall form of our function? Well, overall, what it looks like we're doing is taking an e to some power. The power, though, isn't just x here. It happens to be this whole expression. So what we really have going on is a composition of functions. We have e to the power of a function. Well, what is that function? X squared plus 5. So how do we see this as a composition? Well, what would we do first if we were computing, say, a y value? Well, first, we'd compute x squared plus 5. So that x squared plus 5 would be our inside function, and our outside function would be e to a power. So if we want, we could say f of something is equal to that e to that something. Again, just using that overall structure of what's going on in the outside, and the inside then, what we're putting into that function is our x squared plus 5. So then let's compute the derivative together. So using that chain rule, and again, if you haven't done the previous example that we've just went through together, or if you haven't done it recently, I encourage you to look back at that formula or rule for computing a derivative of a composition. That is the chain rule. So what we do would be the derivative of the outside with respect to that inside. So for us, that would be derivative of e to the x with respect to, or rather not e to the x, derivative of e to that function with respect to that function. So for us, that would just be e to that power times the derivative of what was inside, which is the derivative of x squared plus 5. And recall that x squared plus 5 is the inside function. So that just leaves as is in that derivative. So we just get e to the x squared plus 5 times, well, derivative of x squared plus 5, derivative of x squared is just 2x. Derivative of 5 is just 0, so times 2x. So we would write that as e to the x squared plus 5 times 2x. And there is our derivative.